Hello students, I'm Mwangi Morris from Mount Kenya University, School of Business and Economics, Department of Economics. Today we are going to study our unit Mathematics for Economist 1, and today we are going to study partial derivatives. Now in real life situations are multivariate in nature. That is to say, real life situations are affected by more than one factor. A good example in economics is demand. There are many determinants that affect demand, and mathematically these factors can be represented in a function or in a model using independent variables. Now, when we are considering effects of each of the above or the stated determinants, we would be considering partial effects or partial effects of various determinants to a dependent variable. Now, what is partial differentiation? It is the differentiation of a multivariate function. An example in this case is this function that is bivariate, where y is a function of x1 and x2. Now, partial differentiation represents instantaneous rate of change of a function with respect to any given independent variable. For example, the partial effect of x1 to the dependent variable y. Unlike what we considered in our previous topic, the univariate, where a function had only one independent variable, in this case, our function has got more than one independent variable, and therefore we have to consider the effect of each of the independent variable to the dependent variable. Now, in mathematics, partial differentiation is represented by this sign here. We will use this sign to represent partial derivative. And this one we can compare with the other sign that we used when we were doing the normal differentiation for univariate function. Therefore, for partial derivative, we shall be using this sign. Now, we have rules for partial differentiation. The first rule is the sum and difference rule. The sum and difference rule. Now, in this case, we are having our function y equals to fx1 x2 plus or minus gx1 or x2. Now, in this case, this function has got two functions which are either added or subtracted, where we are having a function 1 fx1 x2 and a function 2 gx1 and x2. They either can be added or subtracted. So when we are doing a partial derivative, we are getting the partial derivative for such a function, we use the sum and difference rule. Now, let's go into it and see how it is done. If you are to calculate the partial derivative of this function with respect to x1, this one, we get the partial derivative of the first function with respect to x1, that is this first function, plus or minus the partial derivative of the second function with respect to x1. We also can get the partial derivative of the same function here with respect to x2. This is how it's done. In this case, we take the partial derivative of this function here, the first function in this function, with respect to x2. We plus or minus. If it was a minus here, we would be having a minus here, but we are considering a plus. The partial derivative of the second variable or of the second function with respect to x2. So the two are the rules that we shall be using to calculate such functions. Let's get an example. Now, find the first derivative of this function here with respect to x1 and the first derivative of this function with respect to x2 of this function 13x squared 13x1 squared x2 plus 21x1 x2 cubed. Now in this case, as I've said, this will be our fx1 x2. This will be our first function, and this one will be our second function. So to get the partial derivative of this function with respect to x1 as we expected here, we now differentiate the first function, this first function, with respect to x1. So this one will be 26 x1 squared, 26 x1x, then x2, as you can see here, then plus the partial derivative of this function with respect to x1. So we differentiate this one with respect to x1, which will be 21 x2 cubed, as is shown here. You also can get the partial derivative of this function with respect to x2. Now, we are to differentiate the first function, this first function in that big function, with respect to x2. So this one will be 13x1 squared plus 63x1 x2 squared. So this is how the function is partially derived, or we get the derivatives of this function for both with respect to x1 and with respect to x2. So if this function had a subtraction sign here, if it had a subtraction sign, then it means that here we would be having a negative and here we would be having a negative. So we have combined both the sum and the difference. So if it was a negative here, then we would have that represented by negatives. Now, rule number 2 is what we call product rule. Now, product rule, this is a rule that we apply when we are getting the partial derivatives for functions that are multiplied. That is, function 1 in this case multiplied by the second function. We are having function 1 multiplied by the second function. How do we get a derivative for such a function? So we use the product rule. Now, to get the partial derivative of this function with respect to x1, we get the partial derivative of the first function with respect to x1, we multiply by the second function, then we add the partial derivative of the second function with respect to x1, we multiply by the first function f. Equally, to get the partial derivative of this function fx1 x2 gx1 x2 with respect to x2, we calculate the partial derivative of the second function with respect to x2, the partial derivative of the first function with respect to x2 multiplied by the second function, then we add the partial derivative of the second function with respect to x2, we multiply by the first function. Let's get an example for us to understand this. In this case, we have to get the partial derivative with respect to x1 and also the partial derivative of this function with respect to x2. For this function, where we are to say this is y equals to 3x1 squared plus x2, this is our function 1, and function 2, function 2, which is gx1 x2, is represented by x1 plus x2 squared. We have to get the partial derivative of this function. Now, if you look keenly from the definition of a product rule, this function is multiplied by this function. So we use the product rule as follows, that dy with respect to dx1 is calculated by getting, we are using this first rule here, f1g, and f1 in this case is the partial derivative of the first function with respect to x1. So the first function is this, so x1 is here, so this one will be 6x1 as it is here. It is multiplied by the second function, and the second function is this one, so we multiply by the second function here, plus we are adding g1. This is the partial derivative of the second function with respect to x1. The second function is this, so the partial derivative of this second function with respect to x1 is 1. We can differentiate this one with respect to x1, you get 1. Then we multiply by the the first function. So the first function in this case is this one, therefore we plug it in that function, and we will have we would have gotten the partial derivative of that function with respect to x1. We also can perform the partial derivative of this function with respect to x2. In this case, with x2 we have said we take the partial derivative of the first function with respect to x2. The first function with respect to x2, so x2 appears here. We differentiate this one with respect to x2, we get 1. Then we multiply by the second function, yeah, f2 multiplied by g. G is this one, we plug it in there. Then plus g2, that is, we differentiate the second function with respect to x2, and we get 2x2, yeah, 2x2. Then we multiply by the first function, and in this case the first function is x1 x2 squared, and that we have derived this function. We would have gotten the partial derivative for this function, both with respect to x1 and with respect to x2. The third rule is what we call the quotient rule. Now the quotient rule ideally is applied when we are getting the partial derivative of functions in which we have the denominator and the numerator and the denominator. Now in this case, a function y, in which case we have the numerator as fx1 x2, and the denominator is another function g x1 x2. Such a function we will be able to get partial derivatives by the use of the quotient rule, and in this case we can get the partial derivative of this function y with respect to x1, whereby we will get the numerator as f1g, f1 being the first derivative of the first function, and g is the second function, and the result, we subtract the partial derivative of the second function with respect to x1 multiplied by the first function, the whole of it divided by the numerator squared. We perform the same for the second variable. We can now do the partial derivative of this function y with respect to x2, and in this case our numerator would be f2g, that is the partial derivative of the first function with respect to x2 multiplied by the second function, minus the partial derivative of the second function with respect to x2 multiplied by the first function, and the whole of it divided by the numerator or the denominator squared. We can get an example for us to understand this. You're given a function, and in this case a function that has got the numerator as x1 squared plus x2 over x1 x2 squared equals to y, and you're expected to determine the partial derivatives of this function with respect to x1 and x2. So such a function, this is what we are saying, we now apply the quotient rule. So let's get the partial derivatives. Now for this one, as we said, you get the partial derivative of the first function with respect to x1, then you multiply by the second function, which was our denominator, then minus the partial derivative of the second function with respect to x1, that multiplied by the function, the first function, and we get now the whole of it over denominator squared. We can perform the same for this partial derivative of the same function with respect to x2, and in this case we are having the result as 1. We are performing this partial derivative, then here to be minus 2x1 x2 multiplied by the first function, the whole of it divided by the denominator squared. The last rule that we are going to apply, is derivative of a function of two independent variables raised to power r. Now these are a case of functions that we call composite functions, in which we're having a function within a function. If you consider this function y, where we're having curly brackets, and within the curly brackets we are having a function f(x1, x2), and the whole of it is raised to power r. This is a case of a composite function. Now when we are considering composite functions, we consider the inner function independently, and we are able now to define the outer function independently, such that we have the inner function. For example, if we say the inner function, let the inner function be u. We differentiate the inner function with respect to x1, for example. The results for it we multiply by the partial derivative of the outer function with respect to u, because the outer function will be y equals to u raised to power r. So the outer function, we shall calculate the partial derivative of this function with respect to u, and the inner function, which is u, will be able to calculate the partial derivative of du dx. So when we multiply the two, we are able to get our partial derivative for the function. Let's get an example for this so that we are able to understand it better. Now in this case, this is what we are explaining, that this is how partial derivatives are calculated with respect to x1, and with respect to x2 we calculate the partial derivative in this manner. Now the rule that we apply here is the chain rule. Students, if you can remember and recall the chain rule in the univariate functions, we apply the same in these partial derivatives to get the partial derivatives for the two for the function. Now let's get an example. You have to determine the partial derivative of this function. Now for us to understand well, if you look at this function, y equals to, in bracket, 3x1 x2 squared plus 3 plus x squared cubed, the whole of it raised to power 5. Students, this is what I mean by a function within a function. The inner function in here will be considered as u, and we let the small function, the inner function here, to be u. We differentiate this function here with respect to x1, and the outer function y is equals to u raised to power 5, we differentiate it with respect to u, and this is how we shall calculate it. We shall get the outer function with respect to u. If this was our u here, we consider this as our u, it would be the partial derivative of y with respect to x1, giving us 5u raised to power 4, because dy du would be 5u raised to power 4 if we did the outer, differentiate the outer function. Then the inner function with respect to x1 is this inner function in here. With respect to x1, it will be 3x2 raised to x2 squared. Now we can perform the partial derivative of this function equally with respect to x2. And in this case, we use the same procedure, but in this case, we shall be partially differentiating the function with respect to x2. And this will give us this result as the partial derivative for that function. Now, after we have performed this the first order condition of the first derivatives, we now can consider the second order partial derivatives. Now, the second order partial derivative, we can explain that the first two order partial derivatives f1 and f2 can be redifferentiated to produce f11, f12, f22, and f21. What does that mean? That when we differentiated the functions once, we got the first order condition or the first order partial derivatives. Now, when we differentiate the first order partial derivatives for the second time, we are able now to get the second order partial derivatives. Now, f11 in this case, it means the second order partial derivative for the function that we initially had differentiated with respect to x1. So we differentiate this function again for the second time with respect to x1. For f12, this function we differentiate it now for the second time with respect to x2. For this function, for this derivative here, f22, we are differentiating this function for the second time with respect to x2, and initially the function had been differentiated for the first time with respect to x2. And the last one here, f22, this function initially had been differentiated for the first time with respect to x2, and now for the second time we differentiate it with respect to x1. So here we differentiate it with respect to x1. Now, what does f11 means? f11 measures the instantaneous rate of change of f1 with respect to x1. The instantaneous rate of change. That how is f1 changing as x1 changes? Now, students, I want you to consider this an important concept, because this concept of instantaneous change, we are going to look at, to use it when we shall be applying these concepts in economics to see the effects, the direction and the effects of this partial, of these variables. Yeah, we shall be considering the effects and the direction. That how is f1, for example, changing as, let's say, x1 is increasing or is decreasing. So this concept of partial, second order partial derivative is very vital, and we shall use it and we shall apply it when we shall be doing applications. Equally, f22 measures the instantaneous rate of change of f2 with respect to x1. It is equally an important concept that we shall be considering, the instantaneous rate of change. That how is f2 changing as x2 is changing? We shall be using that concept in our next chapters. Now, something to note here is that f12 and f21 are referred to as cross-partial derivatives. Cross-partial derivatives are critical concepts that we shall need in our other topics. Therefore, for now, we shall just know how they are calculated, but we shall revisit them and we shall need the concepts in our near future. Now, something to note here is that f12 and f21 are equal. And in a case where you are expected to calculate all the derivatives in here, the partial derivatives, the second order partial derivatives, you only need to know that when you have gotten f12 is the same as f21. it makes your work easier. Now we'll need this when we shall be doing other calculations. These second order partial derivatives, we shall need them when we shall be calculating other variables and other models in the future. Thank you for attending the lesson today. And in our next lesson, we shall look at the application of partial derivatives in economics. This is very interesting because we shall now be learning how to apply the concepts we have learned today in economics. Thank you. Have a nice time.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.